Okay. And first of all, I would like to say thank you to the organizers of this symposium. I'm very happy to have been invited here to Krakow. And as Professor Heller was kind enough to say, I am indeed a historian of science. I'm not a philosopher, I'm not a practicing scientist either. But in my presentation today, I will not really speak as a historian. It will be a very general exposition, including a lot of things in which I'm not an expert at all. So I would like to, I will say a few things about these so-called theories of everything or final theories, but I'll not say a lot about them. I will postpone it to the end of my talk. The subject of limits of scientific explanation is a frightening one, and it occurred to me that in order to get some grasp of the question, it will be useful to ask about its meaning. What do we mean by scientific explanation and the limits of them? So I made this brief and preliminary list of a few things which is useful to have in mind when we speak about these matters. First, I would like to point out, which is rather obvious, that when we speak about scientific knowledge, then in many cases we have knowledge about these phenomena without being able to understand them in the sense that we are not able to explain them. There's a lot of difference between knowledge and explanation. And we don't have to, I mean, it's a very trivial point in a manner of thought to be more concrete. It's very easy to point to the history of science just to give you an indication what I have in mind, but you can find your own examples. Think of the early part of the 20th century when radioactivity was one of the big fields. Radioactivity was very well known experimentally. There was a lot of knowledge, but nobody were able to explain what radioactivity was until the coming of quantum mechanics. We had the same phenomenon when the phenomenon of superconductivity was discovered in 1911. It was researched and people knew a lot about superconductivity. It couldn't be explained. It was eventually explained in the 1950s. And my last example would be the age-old question of the energy generation in the stars, which was finally understood more or less about 1940. The second point is that the question of scientific explanation obviously depends on our chosen criteria for what constitutes an explanation. With an appropriate change of the criteria, we may be able to explain things which previously were inexplicable. I believe this is a somewhat important point, and it's one which I shall return to and exemplify. Then, third, implicitly or explicitly, the question refers to the problems of the domain of science, meaning the territory of reality to which science applies. Are there phenomena or concepts that lie outside the domain of science, or can science legitimately be applied to all aspects of experience and thought? Science, of course, in its usual meaning, is concerned with the natural world, the part of the world that we experience and that we can have empirical knowledge of. It's about what may be called the physical world. After all, the term physics is derived from the Greek name for nature. But then it is possible that the domain of all space-time entities and all experiential knowledge, that this domain does not exhaust reality, and that the in principle observable world is only part of a larger non-physical world to which we have no empirical access, and which therefore transcends the domain of science as ordinarily understood. This non-physical world, whatever it is, may or may not be supernatural in the original sense, the religious sense, but the recognition that there is such a world, that there are phenomena outside science, does not necessarily imply a religious dimension. It certainly did in the old days, when it was taken for granted that there is a divine, so-called empyrean heaven in some symbolic way outside the physical world. But of course, since then, physicists and astronomers have moved away from these kind of thoughts. I'm merely showing you these pictures because they are nice. They are from late medieval and from the Renaissance period, and they are all, in one sense or other, indicating that there is something outside the limits of the stars. Of course, scientists and philosophers have very different ideas of the extension of the domain of science. This is a problem which makes up an important and persistent theme in the history of science and ideas. It's not a problem that I want to enter or that I have time to enter, so I merely want to illustrate it in a sort of superficial way by referring to two very important scientists who had no problem with admitting the limits of science in the sense of a limited domain. This is just an illustration. There is this rather famous quotation by Einstein. It dates from the early 1930s, in which he's spelling out the more or less conventional distinction between the normative and the descriptive aspects, and he's saying, like the majority of scientists and philosophers would say, that science has nothing to say in the normative area. And there is this other and also quite nice quotation by Erwin Schrödinger. It's from a letter he wrote to his colleague Wilhelm Wien in 1926, just at the time when he had discovered wave mechanics, and it sort of reflects his general attitude to life and science. This is the kind of position to which most scientists ascribe, as far as I know, but not all scientists. And it is, just for the sake of discussion, perhaps useful to describe this sort of standard position with a much more extreme reductionism and scientism, which can be found not in many scientists, I'm quite sure, but in a few. This is Frank Tipler, an well-known and controversial, I guess, American theoretical physicist and cosmologist, whose views are undoubtedly not shared by the majority of scientists, but are rather idiosyncratic. But at least it may be useful for the discussion to realize that there are those people who are unrestricted reductionists and who consider this kind of reductionism a virtue rather than a sin. Most of us would probably agree with Schrödinger and Einstein that there are real and natural phenomena that cannot be understood scientifically, such as human emotions. I understand that we will return to that question in the afternoon in relation to the neurosciences, neurophysiology. I am well aware that there are some neuroscientists who claim that human emotions are a kind of epiphenomena, and that they merely reflect electrical signals in the brain. I suppose I will hear more about that. But that is another way of extending the domain of science. But apart from the question of the domains of science, there are questions which have nothing to do with human emotions or the domain, but questions in terms of a conceptual nature. Terms about which we do not even know whether they are meaningful or not, or if they are meaningful, then to which branch of domain their meanings may belong. I would like to mention just 3 of these well-known in a sense, but of course very problematic concepts. First, there is the old question of realized or actual infinities, meaning the question of whether or not there can be an infinite number, for instance, of objects in the universe. Not just a huge number, but a truly infinite number. And not just in an abstract sense, but an actual number, stars or electrons or whatever you have. This is a very old question, and it has been discussed, well, for 2,000 years. There's no answer to it as yet, and it's quite likely that there never will be an answer, at least not a scientific answer. Here we have the great German mathematician David Hilbert in an article from 1925 in which he spells out his belief that the infinite, so to speak, belongs to abstract mathematics and has nothing to do with the realities of the physical world. This is a question that for a long time remained purely academical. It's still academical, of course, but it has become more recently an issue in the standard model of the universe, the flat model, which in combination with the so-called cosmological principle apparently has the consequence that there will be an infinite number of objects. It was also a topic that turned up in the great cosmological controversy of the 1950s in relation to the steady-state model, because the steady-state universe is geometrically flat and it is homogeneous in distribution of matter, so there will be an infinite number in that kind of universe as well. In the modern discussion, whereas some cosmologists seem to be perfectly happy with actual infinities, or at least do not care about them, there are others, such as George Ellis, who have denied the legitimacy of this concept and consider the very concept to be metaphysical and not to belong to physics. Now, if infinity is one of those frightening concepts on the border between physics and metaphysics, and it may well be, so is the, so to speak, opposite concept of nothingness, the concept of absolute void, which is another speculation which has a rich and fascinating history, and one which recently has become more relevant to science, not least after the discovery of the so-called dark energy in the late 1990s, which is usually identified with the vacuum energy as given by, on the one hand, by quantum mechanics, and on the other hand, by Einstein's cosmological constant. Whether this identification turns out to be true or not, it should be emphasized. Here we have the dark energy, which is usually identified with the so-called vacuum energy due to the zero-point energy. But the dark energy is considered to be a reality. It's the explanation of the dark energy which is a big problem nowadays. But what should be kept in mind in relation to these kind of discussions is that there's a huge difference between the modern idea of a vacuum, the quantum vacuum, on the one hand, and then absolute nothingness on the other. The latter concept makes sense to philosophers and theologians, but as far as I understand and as far as I can see, it totally escapes scientific analysis. There is a rich philosophical literature on nothingness, including monographs by philosophical heavyweights such as Sartre and Heidegger. But these works are completely outside science and they do not pretend to give a scientific answer to it. The strange concept of nothingness has not only been discussed in relation to the physical vacuum, and more recently to dark energy, such as I said, but also in relation to the age-old question, which I cannot avoid mentioning, but I'll just mention it, to the so-called creation of the universe, which is, of course, a classical example of the limits of science. So, suffice to say that claims from over-enthusiastic cosmologists to have explained the universe from nothing hardly deserve to be taken seriously. I'm referring to this paper of 1982 by a highly recognized Russian-American cosmologist, Vilenkin, in which he's saying that this particular model explains the origin of the universe from literally nothing. I mean, this is the most unfortunate expression. He doesn't really mean it, but it sounds so good. But then, and I'm relating to the modern discussion in cosmology, perhaps the universe did not come into existence a finite time ago. Perhaps it has existed eternally, and then apparently the whole creation question may not be relevant. The idea that of an eternal Big Bang universe is not contradictory. Quite the contrary, it seems to have experienced a kind of revival. At any rate, we can observe that during the last decade or so, there has been a number, I don't know how many, it's a bit arbitrary, but half a dozen or so, cosmological models which combine the Big Bang explosion, which is inevitable, so to speak, but combine it with a universe which nonetheless has existed in an eternity of time, either in a kind of cycles or in this kind of pre-Big Bang universes, as they are sometimes called. In this case, one can escape the impossible problem of explaining a cosmic creation ex nihilo. But one does not escape the problem of creation, because as it's well known, it is a mistake to believe that the problem disappears in an eternal universe, such as many scientists and indeed non-scientists still believe. I'll just give you one example. I don't know how well known he is, but Carl Sagan, who died some years ago, he was a very prominent American astronomer, and not least a very well-known and very skilled science popularizer in the US television, and he published a lot of books. Very competent person. This is from his last book, The Demon-Haunted World, in which he has this quotation, which is unfortunate because he apparently does not really understand the meaning of the words. So, in effect, what I'm saying is, which is very unsurprising, is that one way or other there probably are cosmologically relevant questions, not maybe questions in cosmology, but certainly cosmological relevant questions that cannot be answered scientifically. Cosmology has progressed enormously, not least in the 20th century, but there are indeed some questions, very, very old, which has resisted explanation, and the reason may very well be because they have no scientific explanation. What I have said so far is admittedly rather superficial, but it's merely to point out that there are fundamental questions related to cosmology and theoretical physics, and indeed to the other sciences, that most likely lie outside the domain of science. Of course, it may be discussed, and it has been discussed, whether these kind of questions are really meaningful. Because according to one school of thought, typically associated with positivism in various versions, they should be dismissed as illegitimate pseudo-questions precisely because they do not have a scientific answer. Now, as I indicated in my introduction, the problem of the limits of science is not only concerned with the domains of science. It also concerns what we mean by scientific explanation or understanding. Not all explanations are scientific, of course, so what is it that qualifies a certain explanation to be scientific and for this reason to be a better explanation than non-scientific explanations? What distinguishes scientific from non-scientific explanations? This, of course, is a big and a complex question, which is very much a question within philosophy of science. I can only deal with it briefly and undoubtedly somewhat amateurishly, but I would like to say a few words about it nonetheless. It's probably fair to say that, at least within the physical sciences, a phenomenon is typically explained by deriving it from or subsuming it under a theory or a principle that must itself be testable. This is essentially the so-called deductive nomological ideal or criterion of explanation advocated by Hilbert, Popper, and various other philosophers going back to the 1930s. And it is significantly a form of explanation which is logically equivalent to prediction. So the essence is that a standard explanation is grounded in a theory that must be testable, and more specifically, at least according to Popper, it must also be falsifiable. We are, for example, satisfied with our current explanation of the galactic redshift because this explanation follows in a non-ad hoc way from a cosmological theory which is testable in the ordinary sense that some of its consequences may turn out to disagree with observations, and if they do so persistently, then the underlying theory will be wrong and it needs to be refuted. While this is a kind of explanation that has been followed in physics with great success, it has some weaknesses or limitations. For other reasons, because the laws from which a phenomenon is explained, these laws are themselves left unexplained. There are many important facts of nature that apparently are contingent and cannot be inferred from fundamental theory. And physicists, at least physicists, do not like contingencies. They want to reduce them as much as possible in principle to zero. And if they cannot explain them, then in some cases, and if they cannot explain them in the ordinary deductive nomological way, then in some cases, in desperation as it were, they may suggest alternative schemes of explanation that change the standards of what constitutes a proper scientific explanation. For example, the coupling constants of the fundamental forces of nature do not follow from the standard model of elementary particle physics, which is the best and the most fundamental theory the physicists have. The same is the case for certain other dimensionless constants of nature, such as the ratio between the mass of the proton and the mass of the electron. So why is the inverse fine structure constant close to the number 137? Why is the ratio between the masses of the proton and the electron close to 1836? And so on. The inability of traditional physics to answer such questions was one of the motivations, not the only, but one of the motivations behind the entropic principle, such as it was formulated explicitly by Brendan Carter in a famous lecture of 1973, and I probably don't have to tell you that this lecture was given right here in Krakow in connection with the 500th anniversary of the birth of Copernicus. It was a conference organized by the International Astronomical Union, I believe. I'm not go really into the entropic principle, and as I have indicated here on my slide, this entropic explanation of the mass ratio between the proton and electron is slightly a caricature, but only slightly. I mean, this gives the essence, or the original essence, of the entropic principle, and the question is, of course, whether this is an acceptable, a bona fide scientific explanation. Carter, back in 1973, was very clear that this was a problematic way of explaining things, that it was untraditional, to say the least. And that is still the situation as far as I know. If the entropic principle is itself untestable, if it does not lead to sharp predictions, but only to probability predictions by assuming a multiverse, a multitude of causally disconnected universes, should it then still be accepted as part of scientific knowledge? The modern controversy over the multiverse, which started about a decade ago and is still going on, I think, is very much about the meaning and legitimacy of scientific explanations. And this controversy has led to various proposals of replacing traditional criteria of theory evaluation with new criteria, which may even amount to a new definition of science. For some years ago, there was in the American science journal New Scientist, no, British is it, but doesn't matter, an article which posed this question: do we need to change the definition of science? Which is a kind of strange question, as if science is something that we define, but perhaps it is. And what they referred to was precisely the question of the multiverse. And we see here two very prominent physicists, Weinberg and Greene. Greene, a well-known string theorist, who sort of say that we are in the midst of a kind of paradigm shift, at least in physics and cosmology, where we have to accept new kind of explanations and what amounts to a new version of science, a new definition of science. So whatever this new definition is, the question of testability is in the very heart of this question. And one may say that the essence of this question is whether a theory that cannot be tested empirically, not even in principle, whether such a theory counts as a scientific one. That is one attitude. A related attitude is to accept the criterion of testability. And almost all scientists agree that a theory must be testable. It's very, very rare to find a scientist who do not accept this criterion. But still, a criterion may be interpreted in different ways. And so what we experience is that there are various versions of the testability criterion. Here I have just a few of them. One may ask whether a theory should be actually testable. I mean, with the current technology or the technology of the near future, or whether testability in principle, which cannot be tested in reality but in principle. There's a lot of difference between these two. Whether it should result in precise and testable predictions of the ordinary kind known from physics and the other sciences, or indirect testability, is that okay? Normally when we speak about testability, and certainly when Popper and other philosophers speak about it, they are thinking of empirical testability. We have a theory giving some predictions. These predictions are tested by means of scientific instruments and so on. But sometimes physicists in some branches of physics, speak about testability in a much more, in a different way. One may speak of testing certain versions of string theory, for instance, and string theory sometimes use the term that they test a model in string theory. What they really do is to check the consistency of this theory, purely mathematical. Should that be accepted as part of it? So we have, as far as I can see, we have a broad rhetorical consensus about that testability is a necessary criterion for scientific theory. But this rhetorical consensus does not necessarily extend to a consensus with regard to scientific practice. There's also the question at what stage of the development of a theory one should require testability. Perhaps a certain theory, when it's just being suggested, is not testable, and it would perhaps be not very smart to dismiss this theory because it's not testable, because perhaps in the next version of it, it becomes testable. So it is a fact, and it has been shown by historians and sociologists, that Karl Popper's famous falsifiability criterion enjoys a broad popularity among astronomers and physicists, but not among all. Much of the modern discussion concerning the anthropic multiverse, Popper, or rather the ghost of Popper, has come under fire by physicists who are dissatisfied with the criterion of falsifiability and who want to substitute that criterion with another and perhaps a better one. I have here two quotations of fairly modern date. Both are from people who are sympathetic to, interested in the idea of the multiverse. Auriel Barraud, a French physicist, and Leonard Susskind, an American string physicist and advocate of the multiverse. They are saying more or less the same. They are saying that, well, we have a theory, it doesn't fit with the normal definition of science. But why should we care? Why should we care what the philosophers tell us that's what is scientific and non-scientific? We know better. Susskind is saying the same thing a bit more dramatically. Why should we care about philosophers' dictum about falsifiability? And then he goes on to say it would be very foolish to throw away the right answer on the basis that it doesn't conform to some criteria from what is or isn't science. So they are saying that let's forget about the demarcation criteria. These demarcation criteria, whether Popperian or not, they are coming from anyway, they're coming from basically from philosophers, and what do they know about science? But one should be careful, and one should be careful in particular with this last sentence of Susskind, because it makes no sense to speak of a right answer without appealing to some criteria or standards of science. Any conclusion about the validity of a theory presupposes some standards of scientific validity. These standards need not be explicitly formulated, but they cannot be avoided, since nature herself does not tell us when such an answer is right. Standards of scientific validity do not come from nature, but from people working with and thinking about science and the accumulated experiences that are revealed in the historical records. So, as pointed out by various critics, there's also a social and indeed a political element in this discussion in the definition of science. Robert Ehrlich, an American physicist, wrote a paper some years ago with this title, in which he is pointing to what I believe is an important question, is saying decisions as to what constitutes a legitimate scientific theory are simply too important to be left to the practitioners of that field, who obviously have a vested interest in it, such as a desire to keep the funding coming. This is a sort of response or critique of the view of Susskind, just as well as the military is too important to be left to the generals, so science is too important in current society to be left to the scientists. So, to end, I'll have to end my talk, and I would like to say a few words, because I said I would do that, concerning the question of the final theory. The final theory and the theory of everything is more or less the same, or at least the two terms are often used interchangeably. The very term theory of everything turns out to be a fairly modern invention. Apparently it only turns up in a scientific context in 1985, and then in connection with strength theory. But of course the idea to have a theory which in principle explains everything is much, much older. It's an idea which I don't know how far back in time it goes, but it certainly can be found during the scientific revolution. Here I have two of the great pioneers of classical science. It's Leibniz up in the left upper corner, who said pretty much the same as Laplace said in his famous dictum of 1796, which is the origin of the so-called Laplace demon. Actually, he didn't speak about a demon, but of an intelligence, but it's very often translated into a demon. And that's what he's saying. Of course, what he's saying is completely depending on the deterministic equations of physics. That kind of determinism, or that kind of classical final theory, has been shut down, basically because quantum mechanics is non-deterministic. But the dream of explaining everything in terms of some fundamental physics theory has remained, and it probably will remain forever. History shows us that all attempts to flesh out such a theory, to formulate an actual theory of everything, has been grand failures. But repeated failures are not enough to kill a dream. And although Laplace's vision is impossible and all later attempts have been unsuccessful, then the dream lives on. I should say that all this talk about the theory of everything is to a very large extent not a talk which goes on in the scientific communities, but very much a talk which goes on in the press, among journalists, and in the media, more so than in the scientific context. But there are scientists, not a lot of them I think, there are scientists who believe in it. One of them is a Swedish-American cosmologist of some prominence, Max Tegmark, who have this quite impressive piece of illustration from this unknown theory of everything belonging to the future, evidently. It should be possible to reduce all the other sciences. Notice not only the physical sciences, but also medicine, psychology, and sociology. But of course there's very little reality. It's a sort of program, and anyway the very idea of an ultimate theory is by its nature problematic. But this is more or less well known, so let me just mention that any theory must necessarily rest on some assumptions concerning entities and concepts. These assumptions being physical, mathematical, or philosophical. There's always be some properties that are not explicable. In a different version, one may say that in some theory, if some theory is truly ultimate, then there cannot be a deeper explanation that covers the theory. It must either be left unexplained, in which case it's not a theory of everything, or somehow it must be self-explanatory. But there's no reason to proceed. I wrote recently, or fairly recently, a book about these things in a historical perspective, in which I have gone through a number of attempts to formulate a series of everything, and it's very clear from this historical review that all such theories, understandably, has been founded on the implicit belief that some current knowledge is final, such as quantum mechanics, relativity theory, or what have you. But by its very nature, a final theory of some particular period of time is unable to take into account for future surprises, future observational and experimental surprises. It cannot predict what will happen in the future. So the concept of the final theory is also part of the concept or claim of an end of science, so to speak. And it's very hard, at least from a historical point of view, to believe in the end of science. At any rate, it has to be understood that such a belief, which has been much talked about, is nothing but a belief. There's absolutely no historical reason to believe in it. Thank you.
Thank you very much. Thank you for your talk. So we have some minutes for questions, remarks, and discussion. Are there any questions, remarks?
I have only one story which was provoked by you. In 1973, I had the pleasure to attend this meeting of the Astronomical Union. Mm-hmm. It took place at the Institute of Physics, and I was at that conference, at that lecture in which Brandon Carter presented his. I remember that very well because during that conference I presented my first international presentation, and I remember even the error I committed in English. I used proposition instead of proposal. So okay, and it was like that. There was a talk. There was a discussion after a talk, and the chairman was John Archibald Wheeler. And during this discussion, he said that I know that here among the audience there is a Brandon Carter, and he has something interesting to say about that. Could you say us? And Brandon Carter stood up and said, "Oh, I can do that, but I would need a couple of hours to prepare because I would to present that in a longer manner." And so Wheeler said, "So perhaps let's wait till tomorrow." And they found the place in the schedule, and next day Brandon Carter presented his talk, and it was the 10 years lecture on the anthropic principle. So it's a historical contribution from.
Okay. Any comments, questions, remarks? If not, I'll thank you very much once again. Okay.